Okay, so we're going to talk about right now acids and bases. So acids, basically, they taste sour, they're corrosive, they react with your metals. So turn blue litmus, red. Oh, and they um, have a pH of less than 7. If we look at bases then, page, when we look at our bases, they taste bitter. They feel slippery to the touch. They neutralize acids. Okay, they turn red litmus paper blue. And they have a pH greater than 7. Okay. Now let's talk about definitions more along the molecular level. So the first definition we'll go through is the Arrhenius definition. And Arrhenius defined an acid as any substance that increases by H plus concentration when dissolved in water. When we talk about a base, so this top definition is for an acid. This bottom definition for a base is that for a base is any substance that increases by hydroxide concentration. Now the hydroxide has to be present in the substance, okay? When dissolved in water. Okay, so examples, of course, for an acid under the Arrhenius definition would be basically hydrochloric acid, acetic acid, sulfuric acid, okay, because they all basically have a hydrogen ion present that can increase the concentration in solution. If we look at the bases based on the Arrhenius definition, they would be like calcium hydroxide, potassium hydroxide, sodium hydroxide. So the hydroxide is present, and that is what lends it to be a base. The problem, of course, is what do we do with substances like ammonia? So ammonia is a weak base. But there's no hydroxide present. So how can we look at bases when there's no hydroxide present in my molecular formula? So Bronsted-Lowry came up with a definition. It's a bit more general. And the Bronsted-Lowry definitions, they depend upon an acid-base reaction, which requires the transfer of electrons. So an acid basically is a proton donor in an acid-base reaction. And the base is the proton acceptor. So now let's go ahead and take a look at a couple of reactions. If I take something like hydrochloric acid and sodium hydroxide, then what we form will be water and sodium chloride. Now I've drawn water slightly differently so we can highlight what we're looking at. So if you consider this, hydrochloric acid increases my H plus concentration. So that's why we define hydrochloric acid as the name states, it's an acid. The sodium hydroxide has a hydroxide, so this is the base. Okay, so this is a classic acid-base neutralization. If we look at it from the Bronsted-Lowry point of view, so what substance donated the H plus? So the substance that donated the H plus is hydrochloric acid. This is the H plus donor. Therefore, under the Bronsted-Lowry definition, HCl is my acid. What accepted the H plus? Well, you can see if you compare what accepted it, the hydroxide here accepted the H plus and became the water. So therefore, this is my proton acceptor, and therefore sodium hydroxide, in particular the hydroxide, is the base. If I rewrite this, I can rewrite this so it looks like this. Suppose I turned it so that it's in reverse. I have my water plus my sodium chloride, and it gives HCl and sodium hydroxide. Again, this too, if you look at my water, what happened here is it donated my hydrogen. Therefore, in this scenario, my water is acting as an acid. My sodium chloride, the chloride accepted the hydrogen. So therefore, according to the Bronsted-Lowry, my chloride is the base. Now the reaction is exactly the same thing. So remember, when we're looking at what is the acid and what is the base, while we're comparing reactants and products, our definitions will apply to the reactant, okay? Now, if we compare this, there's a relationship between sodium hydroxide here as the base and water being the acid. And the difference between the two Here's my hydroxide. And the difference is that we said this was my base. And if we looked at the reverse reaction, this is my acid. The only difference is either the addition or the removal of an H plus. So when you have the same substance with only a H plus transfer occurring between the two, these are called conjugate pairs. This is a conjugate acid-base pair. Hydroxide is the base, and if I add a hydrogen, then water is the acid, the conjugate acid. So how does this apply when we talk about ammonia? Well, look at ammonia. If I have ammonia and I react it with water, what do I get? I get ammonium ion and hydroxide. So what this means is that since my water went from water and it lost an H plus to form hydroxide, this is my acid and this is the conjugate base. If we look at ammonia itself, it accepted, oops, got my plus there. It accepted this H plus, so this is my base, and therefore the ammonium ion is the conjugate acid. So with the Bronsted-Lowry definitions, because we have this relationship now between my reactants and products, it leads to a bunch of different ramifications. So first one is this. We have strong acids. And what happens to the conjugate base? Okay, so if I have an acid like hydrochloric acid, this is strong. Therefore, the conjugate base is the chloride ion. So it goes from strong to negligible. It has no real effect on our pH. Okay. What happens if we have something more along the lines of a weak acid? So let's take a weak acid like acetic acid. If we have a weak acid, then the conjugate base is also weak. So strong to negligible, weak to weak. And finally, if I have a negligible acid, let's take methane, then the conjugate base is considered strong. So strong and negligible, weak to weak. And negligible to strong. All right, let's take a pause here.